Hi all, welcome to Theoretically Podcasting and welcome Bruno.
Hi, Vasu. Thanks for having me here, and thanks for the great channel and the effort you put into this.
I appreciate it. So today Bruno will tell us about some of his work relating optimal transport and general relativity. And I found this very interesting because it seems that they found a sort of thermodynamic story that explains, well, I guess you could call it information theoretic story, that gives some explanation to why Einstein's equations provided certain information theoretic bounds are inevitable in a sort of variety of different settings. So walk us through that, please, Bruno.
Okay. Okay, yes, that's right. As you said, what I'm going to do now is to guide you through this paper we just put in the archive, together with some collaborators, Nicola De Ponti and Andrea Mondino, two mathematicians, and Alessandro Tomasiello. And what we do in this paper, we do a few things. And one, as you said, is to show how you can obtain the Einstein equation from certain information theoretic quantities, in particular from an evolution equation of a certain entropy, which we're going to describe in some details. In particular, actually, the results for the standard Riemannian case or even for the Lorentzian case, these results were already known in the math literature, in particular in the math of the optimal transport. And we're going to see what the connection is in detail. But to just give you a rough idea, the connection stems from the fact that in optimal transport, you are interested in moving a probability distribution. And say you can think of probability distribution as a mass distribution. And your goal there is to move it in the most efficient way, the optimal way. But if you tie the definition of efficiency to the distance that you have in your space-time, then this defines a way to connect this transport to the geometry of the space-time.
Right. So just to be clear, the problem here involves taking two probability distributions that might not even be the same. And we're also talking, so there's the notion of some abstract distance between them as probability distributions.
Yes.
But we're also talking about the evaluation of the probability densities at different points in space. Right, so there's a physical separation.
There is a physical separation. There is also the physical connection is that the fact that there are various, if you just give me the probability distributions, there are various ways to transport them.
Right. So I'm just trying to say that by transporting here, we're really talking about some kind of real space notion.
Yes, indeed. We're going to see the details of that, but that's what I want to say. And the connection with the Einstein equation, the geometry stems to the fact that when you want to transport, you can define your cost of transporting them, say some distribution of mass. The cost you can relate it to the distance, the Riemannian distance or the pseudo-Riemannian distance. And if you do that, you then have a connection between this notion of transporting probability distribution and the geometry. And this is the connection that we're going to exploit to obtain the Einstein equation. We're going to see that prescribing how the entropy changes while you do this transport is enough to completely recover the Einstein equation of the underlying space.
Fascinating.
That's the main relation. And as I said, for the Riemannian case or the Lorentzian case, this was already known in the math literature in a setting that's even more general than simply smooth manifolds, and we're going to see in a moment. A novelty of this work is to also apply all these formulas to the case of gravity compactifications, where these results were not known. And in particular, we will find that there is a different notion of entropy that controls the equation for gravity compactifications, and then characterizing how this entropy changes in a similar fashion, we are going to reproduce the Einstein equation for a gravity compactification. And in doing that, I will also show you how physicists think about the problem, just in the sense that, say some of the results were known in the math literature, but in a math language, which it's very precise and true is the thing you need to do to make sure that what you're saying exists and makes sense. But it's sometimes harder for physicists to manipulate. So we're going to use some formal way of obtaining some of these results. Yes, that's the main connection. And you might ask, why should I care about that? And well, one, I guess, if you're interested in this connection between how to obtain information related quantities from the Einstein equation, that's a way. And there are also some applications of these formalisms. For example, as I say, as we're going to see, this optimal transport language is able to work with more general spaces than simply smooth space-time or smooth manifolds. And in other words, if you use this formulation, you might be able to define the Einstein equation, even in spaces that are not smooth, and say they have some physical singularities, or even more general space, even not continuous space, say discrete space or other. There are classes of spaces that are included in this analysis, and so this provides a way to define the Einstein equation for these spaces. For example, an application of this in the case of compactifications is that we will, as we show in the paper, de-brane singularities. So if you have a de-brane in a supergravity background, this induces a singularity because the supergravity is just the classical low energy approximation of the full string theory. And you see this singularity on the classical fields. And those are included in this class of more general spaces, which are called RCD spaces.
I see.
This means that this is a way to define rigorously the Einstein equation also for these singular spaces where the standard, say, geometric definition might not be well defined.
Right.
Because if you have singularities, the space is not even smooth. What do you mean by Ricci curvature? You're going to see that this is a way to define this. And other than definition in general spaces of the Einstein equation, we're going to see that you can, for example, use this formalism, the math that you work out while deriving it, to prove some properties of solution of the Einstein equations. And there are many things you can ask about a background solution of the Einstein equation. And some of these properties may be, for example, you might be interested in understanding what's the spectrum of fluctuation around the background. And in the case of compactifications, this is the question of understanding what are the Kaluza-Klein modes, what are the Kaluza-Klein fields describing fluctuation around your given vacuum solution, vacuum compactification. And as you're going to see, through this method, you are able to find to put some general bounds on the masses of these fields that hold in very generality. So you don't need to know the background to be able to put these bounds on the masses of the Kaluza-Klein fields. But thanks to this writing, you can show that these hold in general.
I see.
And just from analyzing the equation, not the solution. And this has some application because people have been asking questions about general properties of background of string theories. Like, for example, can you have a very separated Kaluza-Klein spectrum? Meaning the Kaluza-Klein spectrum will start at a much higher scale than the cohomological constant scale, or other things. And we're going to see that we will prove bounds that answer some of these questions in generality.
Very cool.
Okay, so I guess we can start with some of the details. So, we have an introduction here. I didn't explain some things like what the hell I mean by optimal by negative dimension that's written in the title. I'm going to get to this in a moment.
Sure. Let's start where I usually like to start, which is kind of in the middle somewhere.
Okay, let's do that.
It's always the right place to start.
Okay.
It's always useful to have the author to tell you where in the middle you really need to be.
Okay. So, if you want, a way to rephrase our problem is the following. So let's start for the first part of the problem, namely reconstructing the Einstein equation from these entropy-like quantities. So this means that we want to reproduce the equations like 2.1, right? It's just a general Einstein equation is in a general dimension space-time. So we assume that our theory is any theory that low energy reduces to standard Einstein theory with the standard Einstein-Hilbert term in a general number of dimension capital D here. So in this theory, you will get at first order, you get the standard Einstein equations, like which we write in this way. And we want to reproduce this equation. Now, there are various senses in which you might want to reproduce them. One is just try to get this equation in the larger number of dimensions. Another one is asking what happens if you try to reduce the theory and you want to say just reproduce the internal Einstein equations. And that's the second part where we apply these formulas to the compactifications. And okay, let's go back to that. We'll come back to that later. Let's start first with the simplest version of these. And okay, so let's go directly into that. So, as I said, our goal is to reproduce the equation Rmn equal to Tmn, okay? And in particular, for simplicity now, let's consider the Euclidean case. Let's assume that we want to reproduce this equation on a Riemannian manifold. Okay, before dealing with the Lorentzian subtleties. Now, if you want to do that, so we want to do that by using the tools of optimal transport in the following sense. So, let's see what I mean. Now, let's do a step back and define what is the space and the tools we need. So we have our space. We can think for the space as a Riemannian manifold. Let's call it X here. And as I said, it doesn't need to be smooth, actually. All of these can work in a much more general framework or metric spaces, and you can find the details in the paper. But for simplicity of discussion, assume that this is a smooth manifold. Now, on this manifold, assume you are given a probability distribution, which has a certain shape. Let's call it mu0, meaning at t equals 0, this is a certain shape. You can think of it as mu0, something like that, defined in your space. You have your whole space, say, X, and this is a certain mu0. Now, as I said, there are different ways to think about it. You can think of it as a probability distribution for a single particle, so telling where you could find it, or it can be just a mass distribution.
Right.
With a certain total mass. In any case, we are going to normalize it to 1, such that its integral is 1. Now, you can imagine now that each of the bits of this probability distribution, here, each of the bits of mass, will start moving. So this is t equals 0. Now imagine that they will start moving along certain geodesics.
Right.
The geodesics will be different in different places. When this happens, then the probability distribution is going to be distorted. Okay, you will get a different mu at t greater than 0. And we will call this mu x of t. Okay. And now you already see that this is if you track this evolution, you might be able to reconstruct the geometry of the space-time of the space in this case. Why? Because these particles are moving along geodesics. So you might imagine that, okay, if I track every particle, I have enough information to reconstruct what the geometry is. And in particular, you can ask, do I have enough information to reconstruct the curvature?
Right.
If I'm able to do that, I basically reconstructed the Einstein equation written in the form H equals something. And it turns out that this is true. And even more, I will say, interesting is that you don't actually need to follow every particle. You only need to know how a certain functional of this probability distribution evolves in time, what's called the relative entropy. Okay, so the relative entropy, which we're going to define in a moment, is intuitively simply is a measure of how your probability distribution mu is spread compared to the volume form on the space-time. In other words, this entropy will be bigger the more the mu is spread,
right?
And it will be tiny if this mu is very localized, say approaching a delta function. In formulas, this S, let me jump already a bit. In formula, we will have this relative entropy defined as follows. So if I give you a probability distribution mu, now remember that we are assuming that we are on a Riemannian manifold. So we have your Riemannian volume form, I'm calling square root of G. And you can write in terms of a density, this probability distribution mu generic, you can write in terms of density, let's call it rho. So density with respect to square root of G, if you want time the xn, I'm going to suppress the xn in the following. Now, this is the definition of, if you use this notation, this is the definition of this entropy of mu. In this sense, is the relative entropy of mu with respect to square root of G, the volume form.
Right. I see.
So it depends on, so it's the relative entropy of mu, it depends on mu, but also depends on the metric in this way, on the volume form of the metric. Now, what I was saying here is that, as we will see, it's enough to describe the evolution of this quantity to completely reconstruct the geometry. And in particular, we will not even need to really know in detail how this is evolving, but even just an inequality on its rate of change is enough to reconstruct completely the geometry in terms of its quality. That's what you're going to see. As I said, so these results and these methods have been developed in the literature of optimal transport. In particular, there is a very beautiful book by Villani, for which there are some chapters here you can consult to get an idea how this theory works. And it's a 1,000 pages book. And
yeah, those chapters themselves are like another book, probably.
Yeah. But I would say it's very, very well written. It's very accessible, and he has a lot of the history of the fields, references, and it's a very nice book to learn these things. As I said, so mathematicians actually developed this in a more rigorous way that works in more general spaces. What we're going to see is just here now is just a formal way to obtain the similar results for the smooth case.
Right.
And this way of dealing with this probability distribution is sometimes known as octocalculus.
Interesting. Okay.
Okay, so let's get a bit on the details.
Right.
So, what we do is the following. So, now we are in a general space, in particular general metric space, in the sense that we only need to know that we have a space and a distance defined on it. This is more deep. And as I said, that our task is to move a certain distribution mu0 to a distribution mu1. Okay, so let's try again with a simple picture. We have certain mu0. You have a completely different shape mu1. And we want to move every bit from here to here to reconstruct.
Right. So these are distributions again separated in space, and they're not necessarily the same distribution.
No, they only have the same total mass here.
Exactly. So it's just a normalization.
Yes. Because, and this is important, it tells you that in this process no mass is being destroyed or created.
Right. Important. Okay.
And as I say, indeed, these probability distribution in space, but in the Lorentzian case, there will be probability distribution in space-time, or in the case of computification, there will be probability distribution in the internal space.
Yes.
So this is our task. And you want to minimize, so you want to move this stuff, but you want to minimize the total cost of doing that.
Yes.
But you need a way to define the cost. So we define the cost of moving a single bit of mass from, say, x, from a point x to a point y, is given by the distance on this space that you already have, is the distance here. So d gives you a measure of how much it costs to move a single bit of mass from x to y.
Right.
Okay.
So that's the sort of like literal transport aspect.
Yes, this is it's very important. And then what you can do, you then have this optimization problem where you want to know how to move every single bit such that the total cost of doing that is minimized.
Yes.
If you do that, this, what you just said in words, defines a distance on the space of probability distributions.
Good.
Where the distance is precisely what I just described. So is the minimum amount of work that you need to do to move to morph mu0 and mu1, where the cost of moving a single bit is the distance on the space.
Right.
Time,
So
the distance squared.
Physical distance, and then there's also this coupling notion.
Yes. So the coupling is this one. So what I just described in Word, that you need to morph one to the other, you can formalize in this way. You define a probability distribution, a joint probability distribution on two copies of your space, too many x, but okay. And what this pi of xy tells you is where you want to move. So at which y you are going to put the bit of mass that is at x. So it takes as input 2 points and tells you how to move the bit that is at x, how much of this move to y.
Right.
And there are some requirements for all this to make sense, to describe what I just said, which is that the marginals of this joint probability distribution need to be mu0 and mu1.
I see.
This just means that, so for example, if you want to look at the first marginal requirement, meaning it just means I'm saying that I'm imposing on this pi, on this called coupling, I'm imposing that integral of pi xy is equal to our original mu0, and this is just formalize what I said in the following sense. We want all the mass that is ending up in y, all the mass that we are transforming is coming from mu0. So I didn't introduce any other mass in the process.
I see. Good. So this is kind of all now measuring the similarity or dissimilarity in the space of sort of probability distribution.
That's true.
So in that sense, we have both going on. And we have we're measuring a distance in space, but then we're also measuring a sort of similarity or dissimilarity in the space of distributions.
Yes.
And that's what we're trying to minimize to really make this work, is we're trying to minimize
So in other words, a way to rephrase this is that we started from a distance in our physical space, and we obtained in this way a distance on the space of probability distribution on our original space.
Right.
And this distance defined this way is called Tukhantorovich-Wasserstein distance, or Wasserstein distance for short.
I see.
But it's a distance in the sense that if you open a book, you will find that there are various ways to define distances.
So there's even a family of just these Wasserstein distances themselves, right? So there's like a parameterized family of
yes. For example, here I've used the fact that there is a 2 here. I just took the distance square. I can put the distance at a certain power of p. And that will be a different notion of distance.
Interesting.
What is nice about this is that it's quadratic.
Right.
And but in principle, you can consider other options. We are going to use this because it's easy to work with this for our purposes. But that's true. People have considered other distances for other purposes. Okay, so this was why it's entering the optimal transport. And okay, now the step of that we just described. So basically, we had a Riemannian manifold. Let's call it X, and we have with a certain distance d, and we have constructed another space, which is the space of probability distribution. We call this P2 of X, equipped with this metric we just described.
Right.
And we're going to consider this formally as an infinite dimensional Riemannian manifold. This is the optocalculus I was describing.
Right.
It's not literally an infinite dimensional Riemannian manifold. Instead, there are ways to formalize this, and you will find this in Villani's book and in the literature. But for us to have an understanding, we can think of it in this way, to have a simple understanding. Okay, so now we have these two spaces, but you see the space, the probability distribution space is obtained from the original. And we would like also to have a map between different quantities in these two formally Riemannian spaces. In particular, something we would like to have to be able to to do manipulation more easily is the following. I have defined a distance here from coming from a distance here.
Yes.
But on the Riemannian manifold, we have also a metric, which we can use to take scalar product. We would like to see what is the equivalent of the metric here, which is because often it's easier to deal with the metric on the tangent space than with the distance function itself. And so to do that, you need to describe what you mean by tangent vectors on this formal infinite-dimensional Riemannian space. And that's what we are going to do. In terms of this, then we will be able to write down what's the metric on the tangent space. Okay, so how to do that? Oops. So as I said, we were considering now abstracting a bit. We were considering sorry, without the zero. Now, we were considering time-dependent probability distributions. And a time-dependent probability distribution now is just a curve on this space of probability distribution.
Right.
Where T now is parameterizing this curve. And this means that the time derivative of this defines a tangent vector
at that point,
at the point mu of x t in probability space.
Correct. Yes.
Now, we would like a way to characterize this mu dot in terms of quantities we know on the physical space.
Yes.
And how to do that? Well, if you are saying that nothing is being destroyed in the process, it means that we have a continuity equation on our space that's solving, which is here written in 3.2. What this is saying is that a generic mu dot, you can represent it, or actually is related to a vector field on X, our original physical space, through this continuity equation.
Interesting, right.
And this gives you the map that we were needing. This is a map from a tangent vector on X, so a tangent vector on the physical space, to a tangent vector on probability space, which is simply the continuity equation.
Yes.
And we will find useful sometimes in the following to write this tangent vector on X in terms of the gradient of another function, which I'm going to call eta, but we don't need it for now.
Okay.
But it's important. I want you to have in mind this connection.
Good. So just to understand 3.2 fully, would we obtain this by taking mu to be a probability distribution over some x of t, and then if we're describing the evolution of, like, mu sort of implicitly through how x may be evolving, then you would have that c is, like, roughly speaking, x dot.
Yeah, so more precisely is C is a vector field,
right,
which tells you, so again, with the picture, we have the probability distribution, we see changing on time, and C is telling you, is C of X at certain time t, which is fixed now, is telling you at time t, along which direction is moving the bit of mass, which is at point X.
Right, so I see.
And this is the connection, because if I tell you along which direction this is moving, you can reconstruct the rate of change of the wall distribution. If I tell you how it's changing each point.
Exactly, so C is like a velocity.
Yes, it's a velocity vector of each point in the distribution.
Right, very cool. So, and then this statement of saying that it could itself be a gradient is like saying that these that you have some sort of gradient flow type.
Yeah, this is rotational, this vector field.
Right.
That's the proper way of it is closed if you want as a 1-4.
Okay.
And but yes, that's the
very interesting. Okay.
Okay, so
I see. Yeah, you can go on.
So this is the connection that we need. Now, from tangent vector on the physical space, we get tangent vectors on probability space through this very intuitive connection, I would say. And now, this is useful because now we can represent the Wasserstein distance in terms of this psi. Here, before it was a pretty abstract one, in the similar way that the Riemannian distance you can write in different ways. There is a way writing Lily as a minimization problem along all the possible curves, or you can more directly write in terms scalar product and length of the tangent vectors along the curve.
Right.
This is the same thing we are doing, but in probability space now. And indeed, you can show that an equivalent way of rewriting the vast distance is here, is this notion. This is important because now we can easily define what is the scalar product on the probability distribution. So, given two tangent vectors at a certain point mu, remember now a point is a probability distribution. So given two tangent and tangent vectors are time derivatives of probability distribution. So mu1 and mu2 dot are two tangent vectors at mu. And then the scalar product is defined in this simple way. We just integrate over all the space their corresponding vectors on the physical space.
Yes.
And this is the way to write the scalar product on indeed on probability space in terms of quantity in the physical space, and these are easy because then you can manipulate. These are simply vector fields, functions, so on. You can compute things on concrete physical space, but this is what they mean in this sense.
Very nice. Okay, no, that's perfect. I see. So I guess 3.3 intuitively does capture what's going on with this Wasserstein distance, and it'd be a fun exercise to actually work that out. But yes, I mean, given that, then it's quite clear to see how you would get 3.4.
Yes.
Cool.
It's similar to how you go from the distance between 2 points on a manifold in terms of the integral of the total length of the tangent vectors to the length of a single tangent vector per given point.
Exactly, yeah.
That's the
fact that you can do line integral effectively.
Yes.
Compute a length. Yeah.
That's
yeah.
Okay. Now we need an extra step in the formalism in the sense that for now it just described curves in the space and correspondingly I described the curves and on probability distribution and their tangent vectors.
Yes.
These are related to general motion of particles in the physical space. But now we want something extra. We want not simply general curves, but we want geodesics.
Yes.
So what we are going to do now is to do the similar exercise, but now we try to characterize indeed not general time-dependent probability distribution, but probability distribution when they change because the bits of mass move along geodesics. That's what we know. We need to reconstruct the geometry through the curvature. Okay. Now, I'm not going to go to the details here, but what you only need is this equation. This equation is telling you the following. It's telling you the curve in probability space. So with tangent vector mu dot, which as we have seen here, can be rewritten in terms of a function on physical space through the continuity equation. Let me write it down. Something like mu gradient of nu. So this is a function on the physical space. Now, this thing is a geodesic in probability space, meaning that every bit of mass moves along a geodesics in physical space when eta satisfies this differential equation.
Interesting. Okay.
We have an appendix. If you want, you can go through it, or you can look at the appendix where we show that indeed this equation implies that every bit of mass is moving along a geodesic. So it's solving the geodesic equation on the space.
Let's go through that appendix. I think that it would be very helpful.
Okay, let me see if I find the appendix. Blah, blah, blah. Okay, so now, as I said, so we want to show the following. We want to show that if we have a curve that satisfies this equation, which is just simple definition of a curve, we want to show that. Let me see 1 second if I have the other equation here. Want to see where I find the other equation.
Yeah, well, I guess it's referred to implicitly.
Yes, I think so. I want to see if I wrote it down explicitly, but okay, let's see.
We can just write it down at some point. Yeah.
Okay, so now first we need to change a little bit the picture in the following sense. Xi is telling you the bit of mass that's at x, along which direction is moving at time t. But now we want, and this is an approach in which you follow every bit of mass. But now we would like to focus on a single one and follow its trajectory. And to do it is the following. Now, we can do step by step to see how it's related, how this vector field x is related to what I'm calling here zeta, which is the vector field tangent to a single particle.
Right.
And it is as follows. So now imagine that you start from a single bit that it's here at time t equals 0, and that it starts from this point, x naught.
Yes.
Okay. Now, imagine that you just evolve for a tiny delta t amount. Where is this bit of mass going? Well, you can use that by definition. It's moving along xi, and this means that it will end up on a certain point, which is x1, which is here. This is just basically what I'm saying this is what I mean when I say that it's moving along this vector field xi. At first order, it means that it's going to end up in this point. Now, the point is that once it gets to, this means that it's following xi at this time 0, and it ends up being here. This point, I'm going to call it x1. But once it gets here, it's going to follow, the next step is going to follow the vector field. Sorry, there's no one here. It's going to follow the vector field psi at the position x1, because that particle ended up being an x1 at time now delta t, because we started from t equals 0.
Oh, yeah, I see. Right. So it's the initial time plus delta t. Right?
Indeed.
Okay.
And so this means that if you track this the whole trajectory, it means that this is the relation between just continuing this extra step.
That's
it
what
means that this is
trying to encode.
Yeah, so here there is a slightly change of the picture, because one thing is saying at time t where every bit of mass is going. Another thing is focusing on a single one and following it through.
For multiple steps.
Yes.
Yeah.
And this is the connection. So zeta is telling you that. It's telling you now focus on this bit of mass that was starting from a certain point, x naught here, and you will not want to. You want to know what is its tangent vector at time t, the vector tangent to its motion at time t, and this is how you reconstruct it from xi. That's the thing you need. Now we can start take derivatives of these, and we just apply now this. We consider this vector. We just apply the fact that it depends. We want to consider its time derivative to compute whether it's tangent to a geodesics or not.
Yes.
And what we do is this depends on t explicitly and on t implicitly through x, because also x is changing in time. Okay, we just use the fact, expand here, use the fact that x dot in this picture is exactly psi, because it's the direction as you were stressing before. Okay, and now what we want to do, we now convert through eta. Okay, so we had, let's see where we are now. We are rewriting this term here. Okay, and and we take a covariant derivative of 3.5, which is the geodesic equation, if I recall correct. Yes, so we are using this geodesic equation through its covariant derivative. Okay, so
right. So because we have eta dot, and if you want sort of c dot,
exactly
sort of taking the gradient.
the gradient of these. That's correct.
Very good.
Okay, so I need to go down again.
I think c there will just take you. Like if
you are right. We hope so. Well,
hyperlinks aren't all there cut out to be.
Okay, anyway, I think we can. Really? Here should be. Okay.
We're back.
Here we are. So we take a gradient of that, and we are able to substitute a term which is
right.
So xi dot. Also, what's written here is xi dot.
Yes.
We take a gradient and we substitute to the other equation.
So basically, the statement was that eta dot is grad c squared divided by 2 or something like that.
Yes.
And so when we take the gradient of that equation, we're going to have basically, we're basically going to have the gradient of c squared, which is this c gradient, c dotted together, which is c4, the equation c4.
Yes, exactly. And then we commute the indices using the fact that this has is closed.
I see.
Or if you when you lower an index, or if you want the fact that is x itself is the gradient of something, meaning that you can swap the indices. Okay.
Great.
Now
no curl rather. No curl.
Yes, that's what I mean. Okay. Now. We can now substitute this term here, and this means that the time derivative of this zeta is this, but then you can rewrite in terms of this Christopher. This particular combination, you just expand it and you find it's right in terms of this Christopher. But this means that once you expand it again, that you write in terms of this derivative of the metric.
Yes.
Then you remember that psi was just zeta with different dependence, and so what we found is the following: the time derivative of zeta is actually satisfies this equation, but this is the geodesic equation.
Exactly.
On the manifold. So
we found the geodesic equation on the underlying manifold arising from that Hamilton-Jacobi-like equation for eta.
Exactly.
Very good.
And yes. Okay. And as I said, this is for the Riemannian case.
And just to be clear, the Hamilton-Jacobi-like equation for eta came from applying the same logic that we would use for like Whirlline action to get the geodesic equation to the Wasserstein distance. So we treat that like some kind of Whirlline action and try to derive the to minimize that.
If you want, I mean, this also shows that you could have obtained it in the other way around. You could have said, okay, now I have that each bit is moving along a geodesics. How is changing the whole shape? You just trace back these steps in the other direction. You find, okay, it needs to satisfy this equation.
Very cool. Okay.
And so now we have enough machinery that sorry, where we are now.
I think we're on 3.5.
You're right. Okay, good. Okay, so we have defined the machinery. By this I mean that we have defined what we mean by curves on probability space, distribution space. What we mean by tangent vectors there, what is the metric in that space, in this formal Riemannian manifold, and what are geodesics there.
Yes.
Geodesics are probability distribution that change in time according to this formula.
Right.
This formula 3.5, related to the others as we discussed. Okay, now that we know how things change in probability space, we can compute derivatives of functionals, meaning functions in the probability space. That is, since a point in the probability space is a function or on physical space or a probability distribution to be more precise, then functionals on the physical space are just functions on probability space. And this means that now that we know how things change, we can compute how functions change.
Yes.
Okay, and that's what we need to do. We need to do that because a particular function that will be useful for us will be the entropy of the probability distribution. Okay, now you're following the machinery in the sense that we have points which are probability distribution. We will, as discussed before, we are going to parameterize them in terms of a density.
Yes.
With respect to the volume, Riemannian volume form. You can write this just defines what I mean by rho. And this means through this representation, a generic function of f, we are going to represent it in terms of a function of rho.
Yes.
This is just a representation of a function where I'm just suppressing the dxn from the integrals for simplicity. Okay, so functional is defined through a function of its density, of the density of the probability distribution which the function is applied.
Yes.
Okay, and then now we can start compute derivatives. Now you can compute the first derivative of functional. You will put it inside, and you will get the derivatives of these because square root of g is fixed in time. And then you can expand. You will have a derivative of f. You will have rho dot that you can use. You can use the continuity equation to expand.
Yes.
And if you do some manipulation that we do in the appendix, you find that this general expression where p of rho is just a certain combination of derivatives of f and rho itself.
Okay.
And so this comes just by basically computing the f dot and integrating by parts and using the continuity equation. That's the only things we have already all the ingredients. In appendix B, we show some of these manipulations. Okay, and this is giving us the first derivative of a function. Okay, now we can continue. We can compute second derivatives.
Yes.
Okay, we can do it in this way. So we take another derivatives of this expression. Again, now we will have derivatives of this quantity and derivatives also of eta. For derivatives of eta, we are going to use the Hamilton-Jacobi equation, which is the geodesic equation.
Yes.
So we are computing second derivative, assuming that things move geodesically.
Yes, I see.
And you will have many expression. It's a bit lengthy, but it's not hard computation. It's just integrating the parts a few times and recollect terms and using the equation that we just introduced. If you do that, you get this expression here in 3.9. And this is very general. It's telling you for a generic function represented by a function f, this is its second derivative in terms of the quantities that define the motion on probability space and so in physical space.
Yes, I see.
Okay, where again this P2 is just a combination of derivatives of rho on the function. And we define the Laplacian this way. Okay, so this is a generic function. Way to write the second derivative. I think we don't need to go through the details of this. It's simple integration by parts and this kind of thing.
Yes.
Okay.
I mean, it's just worth noting that the pattern of having this rho f prime minus f just continues.
Yes, indeed.
Right? So every time you take a derivative,
yes,
and it's like I think it's because of the fact this is a probability distribution, and just like if you have pure drift, then this is exactly the kind of thing the probability distribution will do under like pure drift in just some Brownian motion, but without the diffusion. Then this is exactly what will happen. And the point is that you need always to have this minus f of rho type term just in case you're changing normalization. So you see like this change will be 0 if this was completely homogeneous to degree 1, right? Which means that like say you just rescaled rho or something, right? Then you're gonna have to land on 0 as a result, right?
Okay.
If the effect of the change is just a change of normalization,
Mhm.
you're gonna have to land on 0 as a result because of the fact that this thing's a probability distribution.
Okay.
You're taking functionals
Okay.
of probability distribution. So that's kind of that actually makes it a little bit easier to understand where 3.9 could come from, because P2 is just the same pattern applied to P.
Indeed.
Right.
And in the Villani books, these are called iterated pressures. So P is thought of in a certain sense as a pressure in a formal sense, and is iterated pressure because it's the pressure of the pressure, if you want. So
okay.
it's
Okay.
okay. Good. Now we are given this expression. Now, in particular, notice this square bracket here, and there is a way to rewrite of this, and which is equation 3.10.
Yes.
So there is a formula known as Bochner formula,
Yes.
which is close relative to the Ricciardo equation. Again, by using this change of pictures, either you focus on how things at each point are moving, or how each bit of mass is moving along its own curve.
Yes.
This connection carries through the geodesic picture, and in particular, it relates with the Ricciardo equation on physical space to this other Bochner equation, still on physical space, but in terms of the other tangent vector field.
Yes.
And we can see something quick about the derivation, but if you just want to get 3.10, it's basically a matter of just commuting covariant derivatives. You see, you will have 3 derivatives acting here now, because you have gradient of eta squared, so you also need to expand the various term, but you have 1 derivative here and 2 derivative here. And you combine them, you commute, and while you commute covariant derivatives acting on vectors this time, you will have curvature terms appearing.
Yes.
And you can play with these commutators and find this equation.
Very cool.
And intuitively, you can see it's a relative to the Ricciardo equation, because it's telling you, indeed, you have a family of geodesics that are changing in time, and you are connecting the behavior of the rate of their change through the curvature.
Okay.
That's what the Ricciardo equation does. You start with a sheaf of geodesics, and you relate their expansion to the curvature.
Yes.
And that's very closely relative to this equation here. Okay, now we can use this equation to rewrite this term in the brackets, and you end up with 3.11. That's the main formula that we need for the for the compactification case. For the simply remaining case, that's the main formula we need.
Very good. Okay.
I will jump ahead a little bit by saying that for the compactification case, what we will find is that there is a different notion of Ricci curvature that controls this behavior, and is a Ricci curvature weighted in a certain sense through the warping, which we'll introduce later. And but mostly the structure is the same. There is a different notion of curvature in that case, not the Ricci one, but the behavior of derivatives are more or less the same. Okay, so this is the main tool we need to rewrite the Einstein equation, at least for this simple case with no compactification, just Riemannian manifold. Okay. And there is a simple connection you can follow here in this part of the paper, where you can change your point of view slightly in the following sense. Here we have describing what is the second derivative of functionals along curves, in particular along geodesics. Right. But this is, you can equivalently rephrase it in terms of what are gradients or Hessians of functionals, because the two are are related. So, for example, if you can convince yourself of this, for example, by just considering a case of a simple functional Riemannian manifold, you can see that actually the derivative along a curve is related to the gradient of f in this simple way. The gradient contract with the tangent vector. Similarly, the second derivative of a function in general is something like that. But if the curve is a geodesics, the x double dot, you substitute using the geodesic equation, you get some Christoffel that reconstruct the Hessian the curvature, I mean the proper action that you will get when you have a metric. And this means that by using connection, that the second derivative is actually the action.
Right.
So you can, if you want, by using this relation, you can change the picture a bit. You can either think of it how the function is changing along the curve, or what is its action. And these are related in this way, just by evaluating the second derivative at the initial point.
Right.
Okay, we will not need it much, but in general, it's useful because, well, one gives the structure of the space, what are the actions there, and one is giving the time derivative of a certain quantity. Okay, now we'll skip this now. So when we will need to introduce for compactification, we will actually need to enlarge all this framework to include weighted measures. So not just the Riemannian measure, but we will need more general measures on our spacetime. And this is related to the warping.
Yes.
So for a warped compactification, we will need all this framework. And this is why we will get different effective notion of curvature. It's not just the simple Riemannian curvature, but effective notion of curvature due to the warping, which also introduced the effective notion of dimension. Yes. What's called in the title in the rest of the paper a negative dimension.
Okay.
We will come to that later. Now let's go straight to the proof of the simple Riemannian case.
Yes, yes.
Okay. So, effective dimension, we will need it later. Let's go now to the entropy and the simple Riemannian case. Now, what we are going to do with all these equations that we just introduced is to prove this identification. So, we are going to see that we can reproduce the Einstein equation schematically in this form through an expression like this, namely by specifying what is the second derivative of the entropy, actually not even giving it exactly, just a bound on its rate of change. And we just need to impose this and require that this inequality is saturated when you consider very localized distribution.
Okay.
So you just need this for general probability distribution and require that it's being saturated when you consider the limit of probability distribution being Dirac delta. So
okay,
just this is enough to reproduce the Einstein equation, as we are going to see quickly now. Okay, so now we apply all the machinery through the function now that we have the formulas for generic functional, but the functional we need now is the relative entropy we just introduced before. So just use the general formula before, where now f of rho, what we call f of rho, is now simply rho log rho with the minus, and we can apply the same formulas that we had before. As I said, this entropy measures how much mu is spread compared to the uniform distribution, where uniform in a Riemannian manifold needs to be defined in terms of the volume form, because otherwise you don't have a notion of uniform, because you want a coordinate independent statement.
Yes.
So you can define you need some measure which is independent from coordinate changes. In this case, will be just square root of g dxn. Oops, sorry. And this is what defines the uniform distribution on a Riemannian manifold. So we compare mu, the generic mu we are considering, to this.
Yes.
And this is why it's called a relative entropy in this sense, or simply Shannon entropy with this idea that is compared through to the standard. Okay. Now we can, as I said, take f equal minus rho log rho and specialize the equation above for the second derivative. If you do that, you get that only this term survives.
Yes.
In particular, this is because that P2 that we had on the other term is actually 0 if you specialize it for this. Yeah.
Okay.
And so you have this simple equation. Now, you can, so as I said, everything we did so far is Riemannian. So you can apply it for just for Riemannian spaces. But it already includes some of the Lorentzian flavor, because you imagine that you have a very simple compactification, meaning just a product.
Yes.
Then, or even just a simple 1 plus n decomposition of a static space-time. So no warping in this case, so no say you cannot describe black holes in this case.
Sure.
But if you just have a simple product, then this formula is enough, because you basically, if you write down the equation in that case, you get that the equations along this, the non-time part of the space-time is simply reach equal a certain combination of stress tensor that is written explicitly at the beginning of the paper. We will come back to that later when you consider more general compactifications. But just as a flavor here, so what we have here now applies to Riemann manifold or very simple product compactification in this way.
Okay.
So not in this sense, it's not purely Riemannian, because if you just remove the time with this decomposition, then you can apply to the rest of the space already. Now, here is the theorem now that we have enough tools. The theorem is the following. You can it's completely equivalent. These two statements are completely equivalent. One, the Ricci satisfies this equation, and two, the second derivative of this Shannon entropy satisfies this inequality.
Yes.
Where T is the same T appearing here. And we also need to, in addition, add that this equality becomes saturated where mu is concentrated at any given point.
I see. Mm-hmm.
And that's all you need. Then is just what you see here is just a more formal way of writing, a more precise way of writing what we mean by localized distribution and so on. But that's the statement. And I can sketch quickly how the proof goes. Okay, because the general way of how the proof works will work also on the other cases. We'll need to define the quantities more careful and variation of the quantities, but the general idea of the proof will work. Okay, so let's see how the proof works. So we want first to prove that 1 implies 2. So we assume the Einstein equation. We want to prove this inequality for the relative entropy. That's pretty easy because, okay, we plug so the Einstein equation that we are assuming, we plug them in the second derivative of S that we had written explicitly here.
Yes.
So basically we just substitute T instead of R. And you do that, and you're basically left with this expression for 0.10. But then you see the second term is positive, it's basically a square. So you can throw it away if you want to get an inequality, and you're basically left with the inequality, with this inequality.
Yes.
Because we removed a negative term minus a positive term.
Yes.
Okay. This proves point 1. The
direction 1.
Yeah. Direction 1, but not completely yet, because the 2 is still, still need to prove the saturation. But to prove the saturation, then we will need a lemma, which is shown in the appendix. It comes from the book from Villani, and this lemma tells you that for actually when the probability distribution localizes to a delta, you can choose eta such that actually you can basically kill this term, the term of this kind. So now we are not assuming, we are not throwing it away because it's positive, but we are doing the following. We are localizing the probability distribution so that this thing simply becomes localized. So this integral localizes at the point, and in that limit, using this lemma, you can actually throw it away.
I see. Okay.
So we have the equality in this case.
Okay.
That for localized distribution, second derivative of S is actually equal to T.
Okay.
That's the first implication. That was easy in this sense. Now we want to prove what I think is a bit the most surprising implication is the opposite. Namely, now we want to say we only know this behavior of the entropy, and we want to obtain the Einstein equations from that. And so at first you notice that it might even look surprising because this is actually just an inequality. It's true that we are requiring that it gets saturated. We are not saying for which point it gets saturated, just for point like, but it's a weak inequality in this sense. And from this we want to obtain an equality that holds for each tangent vector at each point in the space-time.
Yes.
So at first you might think, well, but you don't have enough information from an inequality to get an equality. The trick is that this is an inequality in probability space, which has many more directions than the data space. And that's, for this reason, it's enough to reconstruct it.
Fascinating, okay.
In detail, that's how it works. Now, we have we are assuming that these holds, that 4.9 holds.
Yes.
Okay. So we combine 4.9 with our general expression for the second derivative.
Yes.
And we get this inequality. This is what we are assuming, where EMN is simply the Einstein equation.
Yes.
Is
it's taken by adding it. Yeah, you just added what we already know.
Yeah, so EMN is just defined as RMN minus TMN.
Yes.
And I combined what we knew about the expression and what we are assuming about the inequality.
Yes.
Okay. Our goal is for 11 to prove EMN equals 0 for each tangent vector at each point. Okay. Now, let's first. So we can use, what can we use? We have already used the inequality. Now we want to use that. It's when it's saturated, it becomes an equality. Now, that in the limit where the mu is localized, it becomes saturated. So yes. We take again this limit. So we have this for 11. We take the limit of very localized limit, and then from so this integral means that it localizes at this point x naught, where the probability distribution is localized. Okay, good. Now, again, we will use this lemma that I haven't proven here, but that tells you that in this limit, the second term you can kill the second term for arbitrary tangent vector. And if you do that, then we are left with this expression, because the integral localized at a generic x0, and we throw away the second term. Now, since, as I said, the tangent, the point where we are evaluating this, and the tangent vector is arbitrary, we have basically obtained that EMN as a tensor, if you want, is positive or is non-negative. Yes, just from this expression. Okay, now let's go back, and we know that again the inequality can be saturated if for a certain eta, and sorry, for any point, the inequality is saturated when you are localizing the point for any tangent vector. Now, this means that what I just said implies this equality. Again, if you evaluate it at 411 without using the fact that you can kill the second term, you are just evaluating for a very localized distribution. Yes. And we get 4.13. Yes. From the equality. Now, what we know that the first, so now we see that the two terms are positive, or actually non-negative. The first we just proved. Right. The second, again, is a square. Ah, right. It has to be positive. It has to be positive. Here is everything Euclidean. Yes. And since we have the sum of two non-negative terms equals 0, means that independently 0. Yes. And this proves that EMN equals 0. Very cool. Okay. I see. Nice. And as I said, so this is a formal way of obtaining the statement. In the optimal transport literature, they are derived in a much more rigorous way than what I did here. And also, this formal way works for smooth spaces, but by using the tricks of optimal transport, you can prove it, as I say, for general metric spaces. Very interesting. And there you prove something. It's a bit involved in the sense that you are not allowed to take second derivatives. What you do is the following: you go to a picture in which you consider the action, and then you can define the action even for more general spaces. So we can talk about this later when we discuss deep brains, if you want. But by using that tool, then you basically prove the Einstein equation by proving two inequalities. You first prove an upper bound in terms of t, then you prove a lower bound in terms of t, namely, if you prove that Ricci MN greater or equal than t, then you prove that Ricci MN less or equal than t, then you have proved. Right. But then these are more complicated proofs. These require all this machinery because you're not allowed to take derivatives yes. So there is a whole machinery that's very beautiful and hard, we'll say, for physics to reproduce in this way. This is the formal way to understand what's going on. But to believe the details of these even for the general case, you will need that machinery. Okay. Okay, so and this proves it for the Riemannian case, which means, again, Riemannian or compactification, which are simple product. Once you get rid of the time direction, you focus only on the Einstein equation in the remaining part of the space. And what you can do now, you can generalize this in two ways. One is trying to go to the Lorentzian. meaning try to reproduce this equation in the full space in the Lorentzian setting. This has been done in a work in two works, one by McCann and the other by Mondino and Suhr in the math literature, where they show this fully rigorously. And here there are some subtleties which make the analysis more complicated. The idea is more or less the same, but there are subtleties that come from the fact that this is Lorentzian. And you see, one thing that we used in the proofs is that you can throw away squares.
Right, exactly.
In the Lorentzian, you cannot throw away squares.
Yes.
But there is a way to do it anyway. You need to define some deformation of the standard action, which we are called here these P actions. And if you do that, then you can prove that certain quantities are actually positive definite, and you restrict to those. This makes it a bit more complicated because it requires you to go to a nonlinear setting in which gradients and everything are replaced by these nonlinear gradients that are defined here, which have the advantage that make certain quantities positive. We basically in this paper we show how you do this, and we derive we show all the manipulation that you need to do in the appendix to obtain these proofs.
Okay.
I'm not sure if you want to go through this, but the idea is just that first you focus on massive geodesics, because in Lorentz you need to tell me which kind of geodesics you are working on.
Yes.
So this works now for transportation of massive particles.
Okay.
2, this becomes probability distribution in space-time.
Yes.
And 3, it's technically involved because you need these nonlinear quantities. Otherwise, you cannot use say convexity property of the action if you want.
Right.
But if you do that, then you can basically obtain the same statement, which is the Einstein equation in the Lorentzian case are equivalent to an inequality for, again, the Shannon entropy. Now thought of as a Shannon entropy in space-time.
Yes.
And where these gradients are the nonlinear gradients. But in the paper you find everything, like how to rederive these completely. And then the proofs, once you do that, the proofs follows what we have done in the Riemannian case, because all this machinery was introduced to have things that are manifestly positive, where we need them. And so we can use the same thing. That's more or less the...
Very interesting. Okay.
Okay, so... this is basically a review of what was known.
Oh, not to me. Probably not to the majority of my listeners. I'm gonna go out on a limb and say that it's a little bit cult literature, but no, this is great.
Okay. Thanks. So what we can do is now to apply this to compactifications where we have the new results. And we can also show you some of the things you get out of this formalism, other than just the equivalence.
Okay. So we'll get to the warping now. Yes.
So, as I said, what we discussed so far applies to the whole space-time or the whole space in the Riemannian case. Now, you might be interested in applying these to compactifications, meaning now you have the following problem. You have your higher dimensional theory, which has a standard Einstein-Hilbert term at low energy. So say this can be 10-dimensional supergravity or 11-dimensional supergravity is coming from string theory or M theory. In general, they will have this Einstein-Hilbert term plus certain matter. And this means that the higher the Einstein equation will be like 2.1. Now, instead of considering general solution, you might be interested in vacuum compactifications, which means that you assume that the higher dimensional space time has this form, where this lower d is a lower dimensional vacuum. That is, say, for definite, let's say little d equal 4. And this will be, say, a ds4, or more relevant, ds4, or Minkowski 4. So this little space is just a vacuum, but then on top of the vacuum, you have a general internal space. I'm going to call this internal space, even though there is no need for it even to be compact for this form. I'm just using this language here. So this is an n-dimensional internal space. And however, the most general vacuum solution can also have a warping factor. How is it called? So this is a function in front of the 4D space, which only depends on the internal space.
Right.
Because if it will depend on the external one, namely on the de Sitter coordinates, then it will break its isometries.
Yes.
So what's written here in 2.2 is the most general vacuum solution of a higher dimensional theory.
Right.
And this means that to specify such solution, you need to specify the internal space with its metric and the warping. And that's the most general case. Okay, now what you can do is to try to, you're assuming these answers, so you're assuming that you're interested in vacuum compactification, lower dimensional vacuum, and you plug it into the general Einstein equation.
Right.
You do that, you do some manipulations, and you end up with these two set of equations. Basically, they just come, the first one is a scalar equation, and it comes from the Einstein equation along the external space-time.
Yes.
Since you have maximal symmetry there, it just boils down to one equation, say taking a trace, and this equation, 2.3. If you wish, this is telling you is an equation for the warping. You see, it's a second order equation for the warping. Which gives you the warping in terms of these peculiar combinations of stress energy tensors, which are defined here.
Right.
It's just what you get by reducing the Einstein equation, manipulating, taking traces, and so on. And on the other hand, you also have all the internal Einstein equation, which now are not scalar. These are tensor equations, because you are not assuming any symmetry or nothing at all in the internal space, which you can rewrite in this way. So this tensor made of the Ricci tensor plus derivative of the warping equal to the cosmological constant plus again a certain trace of the original tensor as written here. Now, this means that if you want to use these formulas to rewrite this the Einstein equation for compactification, you need something that gives you this equation, in particular 2.4, which is, if you see, it's a bit more involved than the original Ricci equals something. Now, however, there is this combination on the left-hand side is very interesting. For now, let's give it a name. So 2.6, let's define the combination that you have on the left-hand side of the 2.4. And this means that you have these equations, where I define this constant n to be 2 minus d, where d is the external spacetime.
Yes.
This means that for interesting cases, this n is negative, say at least for d equal 2, d equal 3 or 4 or greater. Okay. Now, what we are going to see is that actually this peculiar combination, this effective Ricci tensor, actually controls the behavior of a certain notion of entropy and vice versa. So specifying the evolution of that notion of entropy, you can constrain this effective Ricci tensor, which in turn then you can use to reconstruct the internal Einstein equations in this way, similar to what we did before. However, this notion of entropy needs to know something about F, the warping, where just to recall, the function in front of the metric was called A in this case, e to the 2a, which is related to F just by R scaling, just because this quantity is more natural. Okay, so our goal here is now to introduce, to obtain equation 2.7a and in particular 2.7b through the same formalism. Now, the interesting thing that you will find is that we are going to use this effective tensor, which has already been introduced in the context of optimal transport, but in particular in the context of optimal transport in negative effective dimension, where this n indeed plays the role of effective dimension, and for us is negative.
Okay.
And this branch of optimal transport is very much new. There is not as well developed as the other ones. And in particular, the equivalence we're going to see is new also in the for the mathematicians.
Okay.
And okay, so I'm going to be brief because mostly of the discussion is going to be similar. We can we don't need this, so you can obtain something more if you're able to bound these tensors, and we will do it when we will discuss applications of this. But for the general equations, then what we would like to do is now to discuss the same formally. So we will be brief now in the following sense. Now, as I said, we are given in this when you have a compactification that you don't only have the metric on internal space with its volume 4, but you also have this positive function e to the f, the warping. So the natural context of discussing all this is in the context of weighted metric measure space, or actually weighted Riemannian manifold, which are examples of a metric measure space, where you consider that you have a metric and a more general measure, which is not necessarily square root of g, but it's also weighted by a certain positive function. In that case, in this context, now it's more natural to define density with respect to this measure on the space, and that's what we will do. This means that in this context, a generic function, you will write it in terms of its density with square root of g, e to the f, and so you will integrate it with the wall measure that you have in the space. Okay, and then you can apply the same machine in the sense that you start computing derivatives functional, and what you end up is basically with the same formula before, but the measure of is going to be the more general measure against which you're integrating, and for example, the Laplacian that you get is a warped Laplacian. Is a Laplacian which defined in this way, the Laplacian of a certain function, and basically that introduces the effect of the warping, namely there is an extra term other than just the second derivative. A way to understand this Laplacian, which will be important for us later because it's the Laplacian we will see that governs the spin 2 Kaluza-Klein modes on the background, but this a way to understand why it appears in this case is just because this is the operator which is self-adjoint with respect to the L2 norm, which includes the e to the f. Okay, that's the way to understand why it appears. This is not the standard, and it appears in this manipulation as you can see in the appendix, because every time you integrate the part, you pick up also the factor of the e to the f. Gradient of that. Yeah. Okay, that's the so. As I say, so this is basically showing that you can basically just do the same manipulation, carrying over this factor of this different measure. So we say the first derivative and again second derivative, and you get a very similar expression, but again with the Laplacian substituted with these weighted Laplacians. What we need to do now is to use the equivalent of the Bochner formula that we used before, or say the Ricciardo formula, to simplify the second derivative term. And you can obtain it as before by commuting, but now you have this different Laplacian. As a consequence of this, you will get extra terms, not just the Ricci tensor, but derivatives of the warping. And this is already a hint that is going towards what we need, because these extra terms are the ones that we will need to reproduce the full internal Einstein equation with warp. It's not enough yet. We don't have the full structure here, but it's telling you why that's how this can appear. Okay, and then you substitute and you get this general formula. And this is what we will use now to prove to obtain the Einstein equations. Here, although we need to make a little pause and discuss what's the meaning of this tensor. So why we're calling it effective dimension, and in particular, why negative effective dimension. So, and you can see it, again, it's easy to see it through the Ricciardo equation. It's analogy to the Ricciardo equation. So very briefly, you know that suppose now there is no warping, purely, even in the Riemannian case, but even more generally. You know that if you have a sheaf of geodesics parameterized by a certain tangent vector to them, you can define their expansion. It's called basically just the divergence of this vector here. And then you can write the Ricciardo equation as here in 3.33. This tells you that there is a bound on how this expansion is changing along the family of geodesic in terms of the curvature and of the dimension of the space-time. This is a standard equation you can get from textbooks. We also derive in the appendix when we discuss an analogy to the Bochner equation. But the reason I'm stressing this is that you see there is a certain way in which the curvature and the dimension enter in bounding how the expansion behaves along geodesics. Now, you can try to ask the same for the weighted expansion, meaning how the measure of your shift of geodesics is changing while they evolve with respect not to the standard Riemannian formula, but yeah,
F transfer G.
exactly. You can write down you do the derivation, and you end up with a formula like this, where this reach Fn is this tensor here, which is the one that we found before in the Einstein equations, and which is again Ricci tensor, second derivative of f, and this peculiar combination of first derivative with this factor. So if you work out everything, you find this equation. This equation is telling you how the weighted expansion is changing along the family of geodesics, and you see it's controlled by this tensor. So we are going to call this an effective Ricci tensor for this warped geometry, and the factor of n appears here, but capital N, which is not the dimension of the space in this case, which was little n, but is this effective dimension, which in our case will be 2 minus d. And so in general, less than 0. So in this sense, you can call it an effective dimension, just in the same way the dimension tells you how shifts of geodesics evolve in time. So comparing 3.33 and 3 and this unnumbered equation, you get an understanding of why you can call it effective dimension, in particular why negative effective dimension.
Yes.
Okay, now we have all the tools already, and we can directly go to the statement. So we need an extra first step, which is the entropy that we need.
Yes.
Okay. In particular, we are going to use this notion of entropy, which is called it's known as Sally's entropy. So if you try to do everything I said before with the Shannon entropy, you don't get the equation that we need. And one of the motivations is that we need something that knows about this effective dimension. And this is what this Sally's entropy does. So this Sally's entropy you can are defined in terms of a certain constant alpha here, which will be related to the negative, so to the effective dimension for us. And you can understand this Sally's entropy as, if you want, as exponentials of Rényi entropy.
Yes.
And in a sense, they are a bit weird as entropy because they are non-extensive because of this, but they can be characterized quite generally, and there are very natural notion of entropy as we discussed in one of the previous sections. And there is a way to characterize them formally, and this is what you get. And this has been introduced by Sallis for other reasons and make an appearance here because of this. Now, what we do now is to consider the time evolution on the internal space of this Sallis entropy. Notice that there is an interesting, I will say, interpretation of the entropy in this case where you have a compactification, which is, suppose you are a lower dimensional observer and you cannot resolve the scales of the internal space. This means that what is a particle for you is actually not a particle. You can think of it as a probability distribution in internal space.
Yes.
If you are not able to resolve the scale, you can apply this to a particle or even to a scalar field, say, or a generic field. You don't know its shape in internal space. So you can parameterize it as a probability distribution if you're not able to resolve those distances. In this sense, this notion of entropy, it's natural in this context of a compactification. Now, start from the Sallis entropy, and then you get this theorem, which is the Ricci tensor satisfies the equation of motion for a compactification, which was that complicated equation, which was Ricci Mn minus Mn of f plus, I don't recall now, the term with the second derivative of f equal lambda plus t tilde, schematically, that we had seen before. Now, this is equivalent to an evolution equation for the Sallis entropy with alpha, this combination of the effective dimension. And this is the statement where you, again, as before, to obtain the complete equivalence, you need also to specify that this inequality is saturated for very localized distributions.
Right, right.
And the proof goes very similarly to before. Just that in this case we have this lambda plus tilde,
Right.
and but basically the idea is the same. And this simply boils down to the fact that if you specify everything in terms of the Tsarlis entropy, you get formulas which are very similar to the ones that we had before. In particular, the second derivative of the Tsarlis entropy, by putting everything together, so the weighted Bochner formula, the weighted second derivative, and so on, as this expression, which is again something like the weighted Ricci tensor plus terms that are squares.
Right.
This is a square, and this other a square because n is negative here.
So it's just positive, right?
And so you throw it away in the proof as before. And more or less the same things work. You will need a weighted version of the lemma that we use, which is also valid, and so on.
Very cool.
And okay. And application you can do with that is that now you can see a nice thing I would say about this identification is that it boils down to this combination of lambda and t tilde. But lambda is the cosmological constant, and t tilde is a certain tensor. You can prove to obtain various results that this t tilde is actually positive or non-negative in many cases. So, for example, if you only have, say, scalar fields or, say, standard matter, meaning positive density matter, like scalar fields, fluxes, even potentials, generic potential, or D-branes, or in general localized object with positive tension, this thing is non-negative. This means that you can even throw it away, and you simply have a full characterization of the Einstein equation, and so even of the properties of the background, just in terms of the vacuum cosmological constant, without needing all the details of the internal space.
Very interesting. Okay.
This we will see a bit more about when discuss the applications.
Yes.
But that's more or less what I want to say. And this relation to the Tsarlis entropy and its negative dimension flavor was also new in the math literature. That's something that what we are planning with our mathematician friends is to write a more rigorous statement than the one we have in this paper. But as I say, the machinery applies, and so also applies then for more general spaces, not just smooth manifolds. Yes, that's more or less.
Very cool. Thank you, Bruno.
Thank you.
Just bring us back. Thank you very much. And indeed, this is a discussion to be continued. I've certainly learned a lot. I'm not going to go read that book about the art of calculus. Maybe think of other things to do with it. But no, this is a very interesting story which connects like some notion of like, there's always these consistency conditions having to do with extended objects of certain kinds, right? And Einstein equations, right? Like the most famous one, I guess, in our field is the one to do with the string theory. Just look at the renormalization group flow equations for the string, that they just tell you something about the Einstein equations and more. But also there's like Jacobson's idea about the Einstein equations of state, which have to do with focusing of null geodesics effectively. That's sort of inferred almost entirely from just Reichheld equation plus some knowledge about the generalized second law, again a bound on its rate of change.
Yes.
And no, here I guess you have a more general setting. I suspect that maybe at least Jacobson's story does fit into this somehow. There probably is a clear relation somewhere. So yeah,
maybe something we didn't explore yet is what happens when you consider null geodesics.
Yes.
In the Lorentzian case, all this is done for massive geodesics.
Yeah,
there are some technical difficulties for the massless case. Maybe that there is some relation more direct if you try to do that. That would be fun to explore. Yeah.
Very cool. Well, thank you, Bruno. And if you have gotten this far, please like, share, subscribe, comment, and I will catch you again on another episode of Directly Podcasting. See you later.